exponential computational improvement by reduction.
Yeah, so the occasion of this workshop made me think a little bit about what had made the most difference in my life computationally, because it's the Computational Challenges workshop. And thinking back over things, I've worked on a lot of things. I've worked on parallel learning. I've worked on sample complexity bounds. I think what really made the biggest difference was learning to think about machine learning in a reduction way. And in doing this, there's been probably 3 cases where I came up with algorithms which are kind of an exponential improvement on what we knew how to do in a semi-optimal way using reductions. So I'm going to talk about this. This is not about any particular result. This is more of a forest talk than a tree talk. But let's just start with kind of where we are. So the field right now is very empirical. So you hear about advances in speech recognition, ImageNet, deep learning, neural machine translation. These are all fun things, but they're not things that are being really driven by theory right now. And when this is happening, it's kind of a question about what should we be thinking about theory-wise. And there are a lot of different theories that exist in machine learning. So let's think a little bit about what happens with reductions. So let me go through some problems that I've worked on. One of them is contextual bandits. So with contextual bandits, what happens is you have some features, you choose an action, and then you see some reward. And now your goal is to learn a good policy for choosing actions given the context. And okay, so it's a good problem. It's easy to imagine that this is a real world problem in many ways. We actually are doing personalized news on MSN using this kind of approach. And it made a huge difference. So in terms of empirical results, we did a reduction, trying to figure out how to, well, let me back up a little bit. For this kind of setting, the first result that people knew about was, I think, the EXP4 paper, which I think was first published in 1995. And it's a pretty amazing paper. But the running time, if you want to compete with a set of policies, is something like order number of policies, which is completely catastrophic in any kind of real-world application, right? So consider enumerating every possible decision tree and then trying to compete with that set. Okay, so we wanted to make things fast. We made things fast. This is the results from the mini monster paper. So the title is Taming the Monster. We compared epsilon greedy as a very simple exploration algorithm, which is suboptimal statistically. This is kind of a heuristic that people use where they kind of train multiple different algorithms and multiple instances of the different algorithms differing by bootstrap sampling. And then you can use that to induce a distribution over actions that you explore from. It's rather slow in comparison because you have to train many different learning algorithms. You can use LinUCB, which is sort of terrible computationally because you have to do some sort of matrix inversion. You can approximate that. We did approximate it. Maybe you could approximate harder than we did. But as you approximate, your performance tends to get worse. You could run our algorithm, which was relatively fast. And then because this was actually a supervised data set that we were only probing for the loss of whichever action we took, you could actually run supervised learning on the same data set in the same way. And then you would see that we're almost getting the same performance as supervised learning, except with only contextual bandit feedback. Okay. So that's a nice result. You can think about the offline contextual bandit setting, which is similar to this, except we're not controlling the exploration. We're just given a bag of exploration data. And now we want to try to come up with a good policy for choosing the action in step 2. Right. And now we can compare different results. And every single line here is actually a different reduction. So the red line is from Bianca-Zadrozny's thesis in 2002. It's using simple importance weighting. The blue line was a paper that I worked on with Lena, where we were looking at using this offset tree technique. I don't want to go into details. And the green line is this double robust approach that we worked on at one time. All of these are operating in a reduction fashion. And you can see that different reductions tend to give you better performance over time as we understand better and better how to solve this problem. Yeah?
What do you mean by reduction?
Yeah, so I can skip to that, or you can just take it on faith. You're familiar with reductions from computational complexity. I mean reductions in that sense, but I mean them in a way which is used for machine learning. And there's a couple changes that need to happen when you switch to machine learning.
So, for example?
So you need to worry about statistics, which you don't have to worry about so much in the computational complexity notion.
An example of reduction you have in mind.
Okay, so let's talk about the red line, which is very simple. So what happens here is you're going to reduce to multi-class classification. So you have, actually you're going to reduce to importance-weighted multi-class classification. So in importance-weighted multi-class classification, you have a label and you have an importance weight, which influences the loss, right? And the way that we're going to reduce is we're going to take our features here, and that'll become the features in the multi-class example. We'll take our action, and that will become the label in the multi-class example. We'll have an importance weight, which is equal to R over P, R divided by P. All right, and then that gives us a transformation from a contextual Bandit example to a multi-class example. That allows us to then apply any multi-class learning algorithm. We can run with that, and it gives us some sort of multi-class predictor, which we can then think of as a contextual Bandit policy, and then we can evaluate its performance. Yeah?
Most of your reductions will be to classification problems?
I mean, some of them are to classification, some of them are to regression. I'm flexible.
What was P, by the way, in the contextual Bandit?
P was the probability of exploring the action. So typically, in order to solve these problems, because you only get feedback about the action that you take, you need to actually explore alternatives. The way, I mean, without context, people use things like UCB, which tend to work less well when you have context, because there's a lot of different correlations to break once you have context information. So typically what happens is you want to randomize the choice of action, and then you need to record the probability of the action in order to debias your estimates appropriately. Yeah?
In the next slide, what are the actions and the context? In the previous one, in the RCV example that you have?
Yeah, so we're taking the RCV1 CCAT or not problem. So this is, so RCV1 is an old predict which category a news article falls in data set. It actually has a hierarchy. One of the top levels of the hierarchy is CCAT, which is like business articles. And so you create a binary classification problem out of that, which is just CCAT or not. And then, so the actions are CCAT or not. The loss is going to be either 0 or 1, depending upon whether or not you make the correct choice. Okay, so let's keep going. Agnostic active learning. This is something that we started working on a while ago, and our first algorithms were remarkably inefficient. They involved, again, enumerating a set of policies. Sanjoy and Daniel worked on the first reduction here. There's several other reductions that have been worked on since. And if you go and you look at what happens, once you have a reduction, you can actually afford to run the algorithm, and you see that you actually get pretty decent results. This is with decision trees, I think, on, I think it's KDD Cup data set, if I recall correctly. KDD Cup 99. So this is the number of labels that you ask for. Let me back up a moment. So active learning is the same as normal learning, normal supervised learning, except we're trying to minimize the number of labels that we request. That's all. This is the number of labels queried for a supervised approach, so it's everything for every unlabeled example that you've observed, and then for an active learning approach. And you see that your performance is, pretty good as a function of the number of labels queried. Okay, so then let's think about one last one. So suppose you want to do just plain old multi-class classification, except you want to do it in time logarithmic in the number of possible classes. Right? So that's a little bit challenging. And again, we have a set of different reductions. The recall tree and the alarm tree are both two different approaches for doing this. And we can compare in statistical accuracy with one against all on these different data sets. And you see that we actually do better than one against all statistically here, worse there, somewhat worse on these ones. This is the big version of ImageNet, by the way. This is the 22,000 class version. Okay, so this is also kind of a fun problem because doing this with gradient descent approaches, which is the algorithm of the day, doesn't actually work. You can't afford to, gradient descent over a set of k things is order k. Right? So it can't be done in logarithmic time. Okay, so let's take a moment and kind of think about what we went through in terms of different algorithms. So I showed you that learning reductions can do something interesting for exploration algorithms, for learning algorithms, for just learning in contextual bandits, for agnostic active learning, and for logarithmic time. And there's other research programs that go on in learning theory. So there's sort of the old PAC learning program, where these settings have not really been addressed much. And there's sort of the online convex optimization approaches. And I didn't know how to express results here, but typically what happens is you make a bunch of extra assumptions about the form of the problem, and then it kind of looks like a contextual bandit problem. So there's like the online convex optimization version of contextual bandits, which is assuming some sort of linear-ish representation and about how the payoffs work.
Sorry, on this slide, for what question is the answer yes or no?
Can you get efficient algorithms using these approaches for these problems? So you cannot, so we don't know how to get efficient solutions using PAC learning for these kinds of problems. At least we have not really studied that. With online convex optimization, there are efficient algorithms that are kind of in the same domain as contextual bandits or as active learning. In active learning, I think in particular, they're the most advanced and they're actually useful. In contextual bandits, I think they're actually not very useful. People don't really use those algorithms very much. And then, of course, you can think back to simple enumeration type algorithms, right? And in enumeration algorithms, you can represent good solutions to these problems. Enumeration algorithms like EXP4, or I guess we think a lot about policy elimination approaches, where you just enumerate all the policies and you start marking them off as soon as you prove they're suboptimal, right? Those kinds of algorithms can give you a good solution. They can compete with a set of policies, but they're remarkably inefficient. So they would also be in the no column. Yeah?
Can you explain how you're comparing sort of, what do you mean exactly by learning reductions being solved?
Yeah, so I'm going to get to what learning reductions are in just a moment. Okay, so if that's the question, then I think we should delay. So, any other questions? Okay. So this is kind of the outline. We've done one. We've discussed why we might want to get to reductions. They allow us to create algorithms for settings that would otherwise be perhaps very difficult to address. And then the question is, what is a learning reduction? Okay, so what I mean by reduction is something where you have, and a reduction is kind of two parts. You have R and you have R inverse, and then you have your base learning algorithm, right? So you have, maybe your goal is to minimize some loss on some distribution producing examples. in the original domain. All right, so you have some algorithm for optimizing some other loss in some other domain, and you need to translate between these two. So you have some way to transform examples or sets of examples from the original domain to the new domain, and then you have some way to transform the predictor that you get out into the starting domain. So that's straightforward. So now the trick is you want to do this in a way such that if H performs well on the induced distribution, then R inverse applied to H will do well on the original distribution. And we need to think a little bit about what well means. So simplest things you could do is just talk about errors. So you could say, look, if I have a small error in my, I call it the base learning algorithm, so in L prime, that will imply a small error in my original problem. Okay, so there's a couple of things which are interesting about this. The first issue that comes up is that you could have a reduction which just introduces noise, just kind of completely wipes out any information about the problem. And then you never achieve the small L prime error condition. And then, okay, so it's kind of like false implies true. So you could run into a situation where you can kind of say anything that you want. So that means that you need to prove that it's actually possible with your reduction to achieve small error if you want to think this way. That's typically true for natural ways of doing it. The other thing is that this observation implies that error reductions are kind of weak for noisy problems. So if we think back to Howe's lecture, he was talking about imitating the expert. Imitating the expert, just straight up imitating, not using dagger, is actually an error reduction. You can say that if you achieve small error in imitating the expert, you'll achieve small error in the overall problem you're trying to solve. But that's not particularly compelling because that small error might accumulate and then things don't work so well. So we might want to have a more refined notion of what a reduction is. Okay, so we can think about regret reductions. In a regret reduction, what happens is you have the smallest possible error rate subject to the noise in the system, and subtract that off from the error rate that you actually achieve. And we call that the regret. And now our goal is going to be to map a small regret in the base algorithm to a small regret in the original domain. So that's kind of satisfying. That deals with the noise issue to some extent. There's still actually a bit of an issue here. Does anybody know? Can you see what the issue is? The issue is right there. That's a min over all functions. And it seems to be the natural thing as far as what we can prove. This is related to your work on different loss functions, right? Okay, so the min is over all functions. That's a little bit different from what we're used to in machine learning. Okay, so that has some implications. It means that if you really want to apply this theorem, the user is kind of responsible for choosing the right hypothesis class. You need to choose a hypothesis class which can actually achieve a small error rate, or which can achieve something very near to that min. Okay, so it also means that there's sort of no notion of information accumulation in this kind of reduction. So if we wanted to talk about acquiring information, which is essential to active learning or to contextual bandit learning, you can't quite do that with this notion of reduction. Right? So So this notion of reduction, if we think back to the sort of the static contextual bandit problem where you had the exploration information already, you can use this notion. But if you want to think about the dynamic problem of actually acquiring the right information so that you can learn efficiently, then this notion of reduction is not adequate. Okay, so you can go one step further. We can try to define an oracle reduction. And here what happens is, let's say we have an oracle which, given some sample, returns the loss minimizing hypothesis within some hypothesis set. So now we have a fixed hypothesis set. And so we have a constrained capacity, as we did not have previously. And now the process of acquiring information becomes reasonable to consider. So for the agnostic active learning reductions and for the dynamic contextual bandit reductions, this is the kind of thing that we were doing and getting good results with. So are there questions about the notions of reduction here? Yeah.
So I guess one question I have is that suppose that you have two different reductions that you're choosing between.
Yeah.
And they both meet the requirements and they both have the same regret transformation property. How do you choose one based on experimentation, or is there something else like?
So let me go forward just slightly. So one thing that you can choose based upon is you can often prove some ratio between the regret here and the regret there. And if you have a tighter regret, often it's a better algorithm. I wouldn't say always, empirically. I think there are elements of what makes a good learning algorithm which are not always addressed by a reduction. But by default, I would kind of go for the one which has a tighter regret ratio. So I think, so when you're working with reductions in a positive way, so this is the other big difference from the computational version of reductions. Here we actually mean reductions in a positive way. It's not like we don't prove hardness here, we prove easiness in some sense, right? Now the danger with proving easiness is that it may not actually be easy in practice, but I think often it is, particularly for natural reductions. So this addresses part of what makes a good learning algorithm. It gives you maybe some of the insight that you need to design something which is going to be very effective in practice.
So it requires some sort of discipline on the part of the person doing the reduction to make sure that the problem being created is easy in some way, right? Because that's not built into the definition.
I think if you want to have a successful algorithm, it requires some real insight into how you're going to create things. I think that there are problems of substantial interest with reductions, which I would be interested in any solution to, just regardless of whether or not it's a crazy solution, because it seems very natural. I'll show you one later. Okay, so backing up, what you prove here is that if the oracle approximately works, or it works, then you have a computationally efficient small online regret solution to the original problem. Okay, so this is actually from several years ago. We have a lot of different ways that we've worked out to do regret reductions. And since then, I think we've spent a lot of our time working with oracle reductions to deal with these information acquiring settings, like contextual bandits or active learning. Okay, so reductions obviously are very good for programming because reductions imply modularity and they imply code reuse. This is exactly the kinds of things that you want in VW, which is a online learning project. It should be a tilde. Reductions are kind of used all over the place, and it's kind of the default way to compose different algorithms. which means that VW ends up being able to solve a lot of different problems. So this is an example of a problem which I think would be of great interest regardless of how you come up with a solution. Even if you come up with a crazy solution, that might help us get to a good solution. Okay, so here's the problem. This actually does have a $1,000 reward that has been around for a while. It's a hard problem. But if you can solve this, I think that would actually be very interesting for the purpose of doing machine learning. So the problem is conditional probability estimation. In particular, given a distribution D over features and example and label, you want to estimate the conditional probability of the label. So in particular, let's just think about the squared loss notion of probability estimation. Okay, so this is straightforward. This is all very straightforward so far. And now the twist is, I want you to do this in time logarithmic NK. And I want you to do it with a constant regret ratio. So if you take away either of these, they're straightforward ways to do this. I can do this in logarithmic time with a non-constant regret ratio. I can do this in linear time with a constant regret ratio. But getting the two of those together seems to be actually very difficult. There's some evidence that one piece of evidence that this might be possible is that if the problem is multi-class classification, if we just want to minimize the error rate rather than doing squared loss, then we know how to achieve this kind of logarithmic time and constant regret ratio. There was a question?
So what do you know for time log k? What's the regret ratio that you can achieve?
I think it's like log squared k. Yes.
Is this in some hypothesis class or something? Or you mean this is parametric, non-parametric?
This is non-parametric. There's no hypothesis class implied.
How
This is just a pure regret reduction that I'm talking about here.
What are you
how do you
reducing to?
define regret if there's no class that you're competing against?
Okay, so we go back when we talk about regret reductions. We say that the regret is the difference between the loss of your hypothesis and the best possible. So some people call that Bayes optimal. And then we want to think about how small regret in the induced problem implies small regret in the original problem. Yeah?
What do you want to reduce to?
Squared loss regression is the natural thing here, I think. So you can just do squared loss regression over one dimension, right?
You said if you replace squared laws with something else, you can work.
Skeptical, but I'm open to consider possibilities. Yeah?
The natural thing is to use something like a logistic loss, which immediately suggests synchronous probability model might make something better.
I'm skeptical, but I'm open to consider. So this is a cold open problem that we published some time ago, probably almost a decade ago now. I would really like to know the answer, and I'm still quite willing to pay.
Oh, the reward is from you?
Yes, I will pay to know the answer to this question. All right, so I talked about the content in this paper, and there's a large number of citations to a lot of work that I consider reductions that are not even my work, which are in this paper. So if you want to go and kind of get the long form of what I talked about, this is the place to go and look and think carefully about what exactly is a reduction and how you can get $1,000. So are there questions?